Hello everybody. Let me welcome you to our lecture dedicated to integration. We will start our lecture from definition of an integral, where we will talk about the area of a linear function, antiderivative, definite integral, and indefinite integral, and then we will study some of integration techniques, such as substitution method, integration by parts, and integration of rational functions. Let's look at the following diagram. Here we can see the graph of velocity versus time. Our velocity was constant and equal to 3 meters per second from the moment t1, which is 1 second, till the moment t2, which is 5 seconds. We know if we multiply our velocity by these time ranges, we can calculate our travel distance, which is equal to 12 meters. And here, these 12 meters actually is the area of the rectangle organized by our v, t1, and t2. So the area under the line doesn't always mean the area, so we have to watch the units. We know that if we take the derivative of our distance, we will obtain the velocity. So here we have the process that is opposite to taking derivative. That is why we need to talk about the antiderivative. We can define our antiderivative by the following definition. So a function f capital is an antiderivative for the function of f small on the interval I if the derivative of our first function f prime of x will be equal to our second function f small of x for all x in this interval I. And also we need to use the following theorem. If f capital is an antiderivative of small on the interval I, then the most general antiderivative of f on I is f of x plus c, where c is an arbitrary constant. We have the following table for different types of functions. So let's look at number 1. If we have a function x to the power of n, our antiderivative will contain the increased power for x, so it will be 1 over n plus 1 times x to the power n plus 1 plus c. Also, we can note, if we look at the numbers 2 and 3, if we have the function sine or cosine, our antiderivatives will contain the function oppositively, cosine and sine. And let's look at the number 6. If we have the function e to the power of x, our antiderivative will be almost the same, e to the power of x plus c. So it means that this function will be the same if we will calculate the derivative or antiderivative. Let's return back to our diagram. So here it is very clear, and we can calculate our area because here we have the rectangle. But what if our function v will be nonlinear? Can we calculate the area organized by our v, t1 and t2? Let's look at this nonlinear function, y equals 1 minus x squared. We need to calculate the area under this curve, which is r. One of the approaches, if we take such rectangles. Here we have 4 rectangles, and we can see that the height of each rectangle is defined also by the function f of x. So we can calculate approximately the area under this curve, and this will be equal to the sum of the height of each rectangle multiplied by the width of each rectangle. And if we denote these values that define our heights through C1, C2, C3, and C4, we can write more general expression. So f of C1 times delta x plus f of C2 times delta x plus so on, where delta x is the width of each rectangle. Let's look at more general case. Here we can see the function, and we can see many rectangles, and we can calculate our area through this sum, where we have f of c case times delta x case. So the height of each rectangle multiplied by the width of each rectangle and their sum. And what if we take our n greater and greater, so our n will tend to infinity? It means that our widths of each rectangle will be smaller and smaller, and finally we can assume that they are equal to each other. So we have delta x for all rectangles for all k. And since we use this n tending to infinity, we can write everything using this limit. So we have this limit n tends to infinity, and sum f of c case times b minus a, which is end of our interval minus the beginning of our interval over n. And finally, this expression, the limit n tends to infinity, and the sum f of c case times delta x. Let's take this expression obtained in previous slide and use the other following notation. So we can see instead of sigma sign, we have integral sign. Our dx corresponds to delta x, and also we have a and b, the upper and lower limits of integration, and these values are the end and beginning of the interval from previous graph. Also, we need to use this theorem. So this theorem is the second part of the fundamental theorem of calculus. If f small is continuous at every point in the interval from a to b, and f capital is any antiderivative of f small on the interval from a to b, then the integral of f of x will be equal to the difference of the following antiderivatives: f capital of b minus f capital of a. If we don't have the limits of integration, our integral will be indefinite. Here we have f of integral of f of x equals f capital of x plus c, where c is any arbitrary constant. And we already know that this is antiderivative for most general case. It means that we can use this table of the rules to calculate our indefinite integral. And also the following rules will be useful for us if our function is multiplied by any constant, or if our function is taken as negative, or we have some or different of two or more functions. Now let's look at the following example. We need to find the general antiderivative or indefinite integral of each of the following functions: a x to the power of 5, b 1 over root of x, c sine of 2x, and d cos of x over 2. Let's calculate a. So we can use formula number 1 from the previous table, where we have n equals 5. It means our antiderivative will be equal to x to the power of 6 over 6. And don't forget about the constant c. Let's take b. Our g of x can be rewritten in the form x to the power of minus 1 over 2. And we use formula number 1 with n equals minus 1 over 2. And finally, we have x to the power of 1 over 2 over 1 over 2. And again, we didn't forget about c. And after simplification, we have 2 times root of x plus c. Sine of 2x. We use formula number 2 and our k equals 2. And this means that we have minus cos of 2x over 2 plus c. And the last one, if we take cosine of x over 2, we use formula number 3, where our k is equal to 1 over 2. And after this application, we have sine of x over 2, and all is divided by 1 over 2 and plus c, which is 2 times sine of x over 2 plus c.